In this video, we're taking on designing a search autocomplete system, similar to what you see on platforms like Google, Amazon, or YouTube. As users type in a search box, autocomplete suggestions appear instantly. This feature seems simple, but under the hood, it's a combination of real-time data ingestion, fast prefix matching, efficient caching, and ranking based on user behavior. We'll look at how to build such a system at scale, handling millions of users, frequent updates, and complex query patterns, while still keeping latency extremely low. The problem is to design an autocomplete system for the search box on Google or Amazon. Here are some good requirement questions to ask. How many autocomplete suggestions should it return? Is the matching supported only at the beginning of the query? Does it support spell check? What's the DU? How does it decide the order of the suggestions? Let's walk through the core components of our search autocomplete system. We start with the data gathering service, which is responsible for collecting user queries in real time. This service aggregates queries as users type and updates a frequency table that tracks how often each query is searched. Next is the query service. When a user begins typing a search query, the service uses this frequency data to return the top 5 most frequently searched items that match the given prefix. To efficiently support prefix-based search and fast retrieval, we use a tree data structure. The tree starts with a root node representing an empty string. Each node in the tree stores a single character and has up to n children, where n is the number of characters in our supported alphabet. Every node represents a prefix or a complete query. We also store frequency information in each node to track how popular a prefix or a word is. Now let's look at the top K workflow. When a query comes in, we locate the node corresponding to the typed prefix. From this node, we traverse the subtree to collect all valid children, essentially, all complete queries that start with that prefix. We sort these children by their stored frequency and return the top K, usually the top 5, results. To optimize performance and avoid traversing the entire subtree on every keystroke, we cache the top search queries at each tree node. This way, we can return results immediately as the user types. This structure helps ensure low latency, high accuracy autocomplete suggestions as users interact with the search bar. Let's dive deeper into the design of our autocomplete system. First, the data gathering service. Rather than updating the tree with every user query, which would be too resource-intensive, we use an aggregator. This component collects and aggregates user queries from logs over a period of time. Then, dedicated workers asynchronously process these aggregates and update the tree in the background. These updates are stored in a persistent tree database, typically implemented using a key-value store. We also maintain a tree cache, which holds a snapshot of the tree in memory for fast read operations. This cache isn't updated in real time. It might be refreshed weekly or based on a specific batch schedule from the tree DB. Next, the query service. It's designed to be lightweight and responsive. It supports AJAX requests so users get autocomplete suggestions without refreshing the whole page. Browser-side caching further reduces latency and improves performance. For ongoing improvements, we sample query data client-side and log it to inform future tree updates. On the tree operations side, updates are deliberately infrequent to reduce computational overhead. We also introduce a filter layer between the client and the tree cache. This layer enforces business logic, such as filtering out inappropriate or banned search terms before suggestions are shown to users. Finally, a note on data imbalance. Some prefixes will naturally be far more popular than others. We must account for these uneven distributions in our design to avoid overloading the system or giving disproportionate visibility to overly popular terms. This deep dive shows how we balance real-time responsiveness with offline batch processing to deliver a robust and scalable autocomplete system.